I think we're ready. Yes. Well, welcome everyone. Welcome to the first of one of our big episodes of 100 Hours from Astronomy in Tokyo and around the world. My name is Cintia Duran, and we are very, very happy because today we're starting one of our big events that we have been working for many months with the collaboration of all of you. So today we're having all sort of activities and troubles and things happening around the world. Thank you all for waiting a few minutes. As you know, we are doing this live, and many of our other events are also going to be live. So something that has been happening is that sometimes, lately, we have been living so many, and we're spending so much time online that we forgot how the entire world works around it, and everything can happen. And right now, we were about to show you some incredible things because we had been prepared a couple of music and a couple of new great ideas that people have been sharing with us. But I forgot my charger in the office, and now my other computer is not working. So we have to quickly, very, very quickly change everything. So now we are back online, so we're very happy. But we were just wanted to share this with you because this is what happens. It is very normal when you're doing an event, when you're trying to engage with people, when you have the incredible luck of participating with incredible women like the women we're going to be speaking with today, is that sometimes not everything has to be perfect. And I think about this because it's something that I've been thinking about lately after hearing these words from a very incredible science communicator that just recently passed away, which was Julieta Fierro. And Julieta Fierro was this amazing astronomer, science communicator from Mexico who her work and everything she did her entire life was about reaching to people, trying to bring astronomy closer to everyone. And she did it in such an incredible way that I'm pretty sure she just connected with every single person that got the incredible luck of hearing her. So in one interview, she actually was talking about how for women, for everyone in general, but for women especially, sometimes we're expected to be so perfect. We're expected to be everything at the same time, because this is what we're supposed to do. And if we're doing a live and we're talking astronomy, we're doing science, we're raising a family, we're doing everything, we have to be perfect. But the reality is that we don't. And this is what Julieta Fierro was telling us. You don't have to be perfect, but you have to be. You have to try. You have to continue, and you have to be yourself. So I'm sharing this because this is exactly what happened to us behind the scenes. And it is amazing because now you're hearing me talk. I'm Cintia Duran. I'm the International Outreach Officer for the Office for Astronomy Outreach at the IAU. But I'm not the only one who's working around this incredible project, which is 100 Hours. There's a great team of incredible scientists, communicators, friends who have been helping us in many different ways, trying to bring these amazing moments close to all of us. And this is one of the things that we want to celebrate 100 Hours with all of you, because we'd like to remember that the sky is for all of us, is something that belongs to all of us. It's not just for a very small part of the world. It's something that we all can cherish, we all can take care of, and we are all part of this amazing planet, and we can all look at these beautiful stars at the same way. So I'm going to stop talking now because I would like to introduce someone who's so amazing and someone who I've been getting to know a little bit more because we've been working with her in this incredible event. So Shannon, if you can come into the live. Hello, Shannon. So I'm not sure how to change gallery. No, I'm gonna see if I can see you. Not right now. I'm waiting to see how it goes. Well, I understand what is happening with her camera. Yes, there she is. I just wanted to let you know that Dr. Shannon Schmoll is the director of the Abrams Planetarium at Michigan State University in the United States. where she has been working to expand both astronomy programming and learning of other subjects under the dome. She earned a joint PhD in astronomy and astrophysics and education from the University of Michigan in 2013. Her research has focused on extending learning beyond the dome planetarium shows. She was a member of the first cohorts of the Astronomy in Chile Educator Ambassadors program and Mission Patagonia to learn about major observations and conservation efforts in Chile, respectively. She was an education research lead in the Big Astronomy Project, which is the main topic that we're going to have today. And she currently serves as the president of the International Planetarium Society, which is exactly why we're collaborating, because this year we're celebrating 100 years of the planetariums. And this is why this particular theme is our central celebration this year of 100 Hours of Astronomy. So hello, Shannon. Welcome.
Good morning. Thank you, Cynthia, and it's been lovely getting to know you and your team as well, working on this event. So I'm not going to talk a whole lot, but I do want to introduce the Big Astronomy Project. You can learn more about it at bigastronomy.org. And this was a large project that was funded by the National Science Foundation that included the creation of a planetarium show, as well as educational activities. And there's additional video content on the Big Astronomy YouTube channel, as well as this video again, if you ever wanted to use it. And for planetarians, if you wanted to get this for your dome, you can get it from Noir Lab and download the show. But the planetarium show and the flat screen version that we're going to show today features major observatories in Chile, because Chile is one of the best places in the world to build these telescopes. And you're going to hear about why when you watch the video. But what's also important, and what that name Big Astronomy means, the title of the show is Big Astronomy People, Places, Discovery. Because when we are, the amazing things that we see and we learn about and the discoveries we make about the universe, those things have to happen through collaboration. And we have to place things in certain locations where it's ideal for observing. And there's many people with many different skill sets that go into keeping these observatories running. And these collaborations are often across multiple countries and agencies and universities and researchers and technicians and engineers and writers and so on. And it is a really big operation in order to get these amazing discoveries. And so you're going to hear from some of the people that work at these observatories. You're going to see some of the incredible places where we've built them, and you're going to learn about some of the discoveries. And then at the end of the show, there's going to hint at the future observatories that are coming through. You're going to see one get built up in sort of a time lapse. And that one is the Rubin Observatory, which you'll hear more about afterwards from our other guest, Ardis Herrold. And so, which is one that I'm really excited about. It's not named in the show because we had to finish the show right before they changed the name. So we didn't put the name in, but it's a little teaser for what you're going to hear right after. But I'll stop there. I'll lurk in the chat, so if anyone has questions, I can answer them there too. But thank you, and enjoy Big Astronomy, and stick around to hear about the Rubin Observatory afterwards. Thank you.
Okay, so we're now going to play the video for you. The video is around 20 minutes long. It's an incredible video that you can, it's going to be kind of a teaser of the things that you can have or that you can share with Big Astronomy. Big Astronomy is a project that is open to everyone to use around the world. It's a dome project so that any planetarium in the world can use it. So this is an incredible resource, educational resource, astronomy engagement resource that many communities and many institutions have come together to develop to bring us these views of the amazing, greatest observatories in the world that are in Chile right now. So can we start playing it? Yes.
I always marvel at the night sky. It's beautiful, of course, but light from the universe also helps us unlock its secrets. My name is Ayala, and I study stars. We have learned that almost every star we see hosts one or more planets, and we're finding more planets all the time. So for me, the night sky is filled not with distant, lonely stars, but with countless families of planets. I want to share some of these family stories with you, where they come from, how they take shape. But I also want to introduce you to where I come from. A place where astronomers study the sky, with the help of amazing technology and even more amazing people. A place where people have experienced a strong connection to the night sky for millennia. I want to introduce you to astronomy in Chile. Chile lies on the west coast of South America, a long, narrow, mountainous country. The Pacific Ocean lies to the west, the towering Andes Mountains to the east, and the Amazon rainforest to the north. Chile is perhaps the best place in the world for observational astronomy because of its special climate. The Andes block rain clouds from the east, while currents in the Pacific Ocean bring cold waters north from the Antarctic. Along the Chilean coast, the air temperature drops, and as the cool air sinks, it loses its moisture. These factors combine to create stable dry air over Chile's coastal mountains with few clouds, perfect conditions for astronomy. Many major telescopes dot Chile's mountainous terrain. We will visit just 3. These observatories are looking at places in our solar system and beyond to help astronomers understand where planets like ours come from. Standing on the side of this mountain, you can understand why it was named Cerro Tololo, which in the Aymara language means at the edge of the abyss. Cerro Tololo Inter-American Observatory is home to dozens of telescopes. Let's take a look at the largest, the Victor M. Blanco telescope, with a primary mirror 4 meters in diameter. Astronomers designed this telescope to observe the same kind of light our eyes can see. It's an optical telescope. Light enters the large opening and bounces off the giant mirror. It's the first thing the light hits, so we call it the primary mirror. The bigger the mirror, the more light it can collect. So astronomers like to build large telescopes to gather as much light as possible. The shape of the mirror focuses light on a giant lens, more than 1 meter across. That lens is part of an amazing instrument called the Dark Energy Camera.
The Dark Energy Camera has 62 science detectors, one of the biggest cameras in usage in the world right now.
Marco Bonatti is the first of several people we'll meet who keep these observatories running. As an electronics detector engineer, He's responsible for what happens inside the instrument.
You need to be very careful that they are clean all the time, because otherwise you have all sorts of stuff deposited in the surface, and the surface is especially coated. Basically, we want to avoid any dust particles. So in the clean room, we have a controlled environment. We can control the amount of dust inside by basically you having filters and positive pressure that keep the dust out. All the light that the telescope gathers goes to a single point, basically. And this point, you put a detector. So the detector you put there depends on the science you want to do and the instrument, a lot of factors.
Once the instrument is out of the clean room and mounted on the telescope, other team members help make the observations.
My name is Jacqueline Cerón, and I work at Certolodo Inter-American Observatory. My position is night assistant. This means taking care of the instrument and having the telescope ready, taking calibrations, and making sure that everything is working fine. And during the night, operating the telescope, which means moving the telescope to the position that the observer wants, and making sure that everything is working correctly. What I really like is to learn in general how the telescope works, how it takes data, and all these different systems that are interconnected and that, accomplish such a huge task, and all the engineering involved. It's amazing.
Let's hear more from Kathy Vivas, a Venezuelan astronomer living in Chile.
I am part of the support team of one instrument in the Blanco telescope, the Dark Energy Camera, which is a wonderful instrument. It's special to make surveys to cover large portions of the sky. As part of the support team, we make sure that the camera is producing science quality data that is ready for astronomers from all around the world to come and do their science projects with the telescope, and that they can achieve their science goals with this instrument.
The Dark Energy Camera was designed to peer into the farthest reaches of the universe. But because it can observe a large portion of the sky, it also helps us search for objects much closer to home. Leaving Earth behind, we see the orbits of planets around the Sun. Mercury, Venus, Earth, and Mars. Jupiter, Saturn, Uranus, and Neptune. But our solar system includes many other objects, not just planets. Astronomers have used the Dark Energy Camera to find numerous small, icy bodies in the outer reaches of the solar system. We have tracked thousands of these objects, which reside far away from the Sun, past the most distant planet, Neptune. They make up what's called the Kuiper Belt. Billions of years ago, everything we see here likely revolved in the same plane. But the massive planet's gravity tugged the lightweight Kuiper Belt objects into different orbits. They now travel far above and below the plane of the planet's orbits. Each tiny icy world we discover helps us answer questions about the history of our solar system. What did it look like billions of years ago when the planets were taking shape? We can't go back in time, but we can observe other planetary systems in the process of forming. This work requires our most powerful telescopes, so let's return to Chile. We're heading to a mountain called Cerro Pachón. Only about 20 kilometers from Cerro Tololo. Here we find the Gemini South Observatory, which began viewing the sky in 2002. Inside the dome, we can see the giant telescope with a mirror more than 8 meters across, more than twice the diameter of the Blanco telescope. This giant mirror must remain highly reflective, which means it needs cleaning every week. Such a big job requires a lot of teamwork.
My name is Vanessa Montes. I'm an electronics engineer. We have different disciplines like optics, mechanics, electrical, software also. We all work very well, and it's a lot of team effort and a lot of collaboration between everyone. And I think that that's very positive. The more you can encourage people to participate more creatively in the different projects that we do, it's a more collaborative work environment.
Cooperation on Gemini extends around the globe. Astronomers rarely travel to Chile to use the telescope. Instead, they telecommute. Here, in the Gemini base facility in the coastal town of La Serena, nearly 100 kilometers from Cerro Pachón, technicians can operate a special instrument that looks at young planetary systems, called the Gemini Planet Imager, or GPI. Almost 10,000 kilometers away, at Stanford University in California, observers see the same displays and guide the work with GPI. Astronomers need somebody they can trust on the other end of the line, and that's where Alicia Shugart, Science Operations Specialist, comes in.
We operate the telescope at night. We take data for the astronomers who have all contributed proposals for science. I really enjoy observing. I think about it as if these photons that literally are billions of years old are arriving, and I'm seeing them for the first time.
Not all photons are billions of years old. Many were created more recently, closer to home. Light detected by GPI reveals what happens when planets form around nearby stars. We can imagine traveling to one such place, so far away that its light takes more than 60 years to reach us. This star is more massive and much brighter than the Sun. The star and its planetary system are less than 30 million years old, mere infants compared to our own middle-aged solar system. Dust and debris form a disk around the star. Some tiny objects in this disk will end up like our Kuiper belt, icy bodies at the edge of the system. GPI allows us to peer into the center of the disk. Astronomers then use computers and the laws of physics to simulate what might be happening. We have discovered one giant planet, more than a dozen times more massive than Jupiter, whose gravity has sculpted the dusty disk into a warped spiral. Could something similar have happened in our solar system billions of years ago? For the next part of the story, we must now travel much farther north in Chile, to the Atacama Desert, one of the driest places on Earth. home to a collection of 66 radio antennas, the Atacama Large Millimeter Sub-Millimeter Array, or ALMA. The skies of the Atacama Desert are famously clear, and people have observed the sky from here for millennia. David Barrera is president of the indigenous community of San Pedro de Atacama.
I feel that the cosmos walks with me. It walks with you, with humanity. It is part of our life. We humans are nothing compared to what the great cosmos is. That is why we are part of the cosmos. We walk together. We make up a single unit. That is the marvel and wisdom of the native people in regard to the cosmos. An ALMA's invitation to the indigenous community is in some way to unite scientific knowledge with indigenous knowledge.
Astronomers have come to this unique spot on Earth to build an array of telescope antennas that benefit from the clear, dry skies 5,000 meters above sea level. These giant antennas work together, like a single, enormous eye observing the sky in unprecedented detail. And they can work both night and day. Each dish weighs about 100 tons. And they need to move from place to place, both to make different kinds of observations and to receive maintenance when needed. Alfredo Algueta is one of only 4 people trusted to operate the transporters that move the telescopes.
The transporter has just one basic work that is designed to do, and it's move this big radio telescope from one point to another. When you're doing the maneuver of trying to load the antenna or unload the antenna, you have to do it with the remote. But when you're doing the translation from one point to another, you have to do it from the cabin. So every time that an antenna needs like a big fixing or anything, we try to bring it down, but it takes a lot of coordination to do that. It takes around 5 hours, driving 5 kilometers per hour.
Once the antennas are in their correct locations, they collect a huge amount of data, and they work as a network. Data from each antenna is compared to data from every other one. Celia Verdugo, an astronomer and data analyst, collects and studies these observations for astronomers from Chile and other parts of the world.
The kind of light we are collecting from the sky is a light that is emitting in radio wave shape, you see. We are looking at the parts of the universe with the lowest temperature, and because of that low temperature, they emit their energy through radio waves. We collect that signal, and from that, we can get either spectral information, or we can also get images of the source we are observing. And we are taking data for projects that are breaking the limits of what we know, going beyond the limit of our knowledge. That is really fascinating, yeah.
One of the ways ALMA has revolutionized our view of the universe is by giving us a close-up look at young planetary systems. Here, we are seeing not just the leftovers of planet formation, but the actual disk of material from which planets take shape. This is ALMA's image of BDS 70, a very young star, less than 10 million years old. Its debris disk looks more like a ring of dust surrounding the star, with a large gap where at least one Jupiter-sized planet is forming. That planet has a small disk of its own, where moons could be forming around it. Here, we're seeing the results of a computer simulation, which we can compare with data from ALMA and other telescopes to help astronomers understand how planets grow. Perhaps our solar system looked like this billions of years ago, a family of planets taking shape. Pioneering work in astronomy requires investing in the next generation of telescopes. When completed, this telescope will observe the entire visible sky every few nights. It will generate 20 terabytes of data each night, twice as much as the Hubble Space Telescope generates in a whole year. All the data will be made freely available to the world, enabling anybody to make the next great discovery. The future of astronomy lies in all our hands. That's why I enjoy meeting with the students of all ages. I hope some of them will grow up to work with me at one of Chile's great observatories or elsewhere in the world. All of us you met today come from different backgrounds with many different talents and skills to contribute. We invite everybody to look, to learn, and to enjoy astronomy. We hope to share the wonder of the sky and the excitement of discovery with the whole world. If you'd like to meet more amazing people and hear more stories about big astronomy in Chile, visit bigastronomy.org, where you will find live conversations with observatory staff, exclusive behind-the-scenes content, and educational activities.
Wow, this was really, really amazing. I've never seen it. I mean, I've read about it, and I've been seeing a couple of clips of the research of the different observatories, but I've never really seen the entire material, Shannon. I think it's an incredible work that many people have been doing.
Thank you. And yeah, this has been distributed to many planetariums. So if you want to see it in the original planetarium form, find your local planetariums and see if they have it and if they're running it. But what we're going to do now is move on to a talk about that telescope I hinted at the end that was getting built up. That was the Vera C Rubin Observatory. And so we're going to hear more about that from Ardis Herrold right now. And Ardis Herrold is a senior education specialist for the NSF-DOE Vera C Rubin Observatory. She leads the Rubin Observatory Education Program, which includes creation of classroom investigations and teacher professional development. Prior to joining Rubin, Ardis taught physical, earth, and space sciences at the high school and college levels, and she's worked in planetariums and observatories. She's also a lifelong amateur astronomer and has her own personal observatory in Tucson, Arizona, where she observes deep sky objects, comets, and supernovae. On a more personal note, Ardis, I first met her. I told her this last year, but I first met her and saw her and heard of her work when I was at a meeting of the Michigan Science Teachers Association, and I was there actually talking about astronomy and observatories in Chile. And she won an award, and the sheer joy that people had in getting to celebrate her and to give her this award, I think speaks volumes to how wonderful of an educator Ardis is. So I'm always in awe of her and so glad to have her here. And so I'll let her educate us now on the Rubin Observatory.
Yes, yes, please.
Thank you, Shannon. Okay. Well, welcome, everybody. I'd like to, first of all, just mention to you that, like many of you, I have been involved my entire life in astronomy outreach. So if you have any questions or comments about this after the talk, even though my talk is more focused on the Rubin Observatory and its technology and its science, I'm happy to entertain those. So you had a brief introduction to Rubin Observatory at the end of Big Astronomy, as Shannon just mentioned. We are jointly funded by the National Science Foundation and the U.S. Department of Energy Office of Science. And like many observatories in the U.S., we have counterparts in Chile because, as Shannon mentioned, the incredible dark skies there, the quality of the air. So we're located at about 30 degrees south latitude in the area of the Coquimbo region of Chile. Closest town would be, or closest city would be La Serena. And our altitude is about 8,800 feet. So we're not super high like Alma is into Atacama, but it's very good sky there, very stable and dry air. Okay. I'd like to mention that our observatory was first named the Large Synoptic Survey Telescope, but in 2019 we were renamed in honor of Dr. Vera Rubin. Vera Rubin was the first scientist who provided convincing evidence for dark matter. She didn't propose the idea that had been around for decades before she began her research, but she was able to bring the astronomical community over to actually accepting that this dark matter was a real thing and not just a crazy idea. Dr. Rubin especially dedicated a lot of her efforts as a scientist to being inclusive, to bringing in everybody who wanted to do astronomy. She was a strong advocate for women in astronomy. She herself had encountered many obstacles because she did her research at a time when women were not well accepted as astronomers. But we love the fact that she once said anybody who wants to do science should be able to do so. And we've really adopted that attitude in our education and public outreach to make our observatory data available to anybody who wants it in whatever form and level that they should be able to receive it. And this is the fact that this observatory is the first major public U.S. observatory named after a woman astronomer. We're very, very happy about that. So I'd like to talk to you today about some of the transformative ways that the Rubin Observatory is going to change not only the technology that we use to study the sky, but also the science. And a lot of this technology transformation has already happened because it had to be created in order to build our observatory. You notice the Rubin Observatory has an unusual shape. So if you look inside of the observatory, the dome where the telescope is located is at the high point of the observatory, but there's this long promontory shoe-shaped kind of extension. And that's where we have a lot of the facilities we need to support the observatory. For instance, a machine shop, the control room. We even have a place to recoat the mirror. So this will really increase the efficiency of operations for our observatory because we won't have to take out pieces and transport them to somewhere else to have them worked on or upgraded. And that's the observatory is also built into the mountain in an orientation that takes advantage of the prevailing winds. The LSST camera is the largest camera that has ever been built for astronomy. It's the size of a small car, and it weighs about 3 tons, 6,000 pounds. You can see it's here in one of the rooms being prepared for testing. The camera itself has a number of interesting features. It has the largest optical lens ever built. It has a Guinness Book of World Records for that. It's also the largest camera ever built, or the highest sensitivity camera, highest resolution built with 3.2 gigapixels. There are 6 filters that will be used in tandem with the camera to study the sky from ultraviolet to infrared wavelengths. And the camera was developed primarily at SLAC National Accelerator Laboratory in California in the United States. The images produced by this camera and telescope system are huge. Each one covers an area of about 45 full moons. So if you imagine looking at the constellation of Orion and drawing a circle around the stars of Orion's belt, that is about the size of one image. So these are just incredibly large images compared to a typical telescope image. Because of that, we're able to cover much more sky every time we take a picture. And all of these images will be 30 seconds long. So these images, because they're about 100 times larger than other telescopes, give us the advantage of being able to collect a lot more data more quickly. So as you see here, it would take 1,000 years to complete what we will do in the first 10 years. The way to think about how large this camera's resolution is that if you wanted to display one image at full resolution, you would need almost 400 4K HD TVs stacked side by side. So if you can imagine the surface area of that, it would cover just half, a little bit over half of a basketball court. Now, that incredible camera is mounted as part of the Simony Survey Telescope. We renamed the telescope recently as a nod to the Simony family, who donated $30 million to kickstart the development of our telescope's mirror. And I'll be talking to you a little bit more about the mirror in a minute, but this is a wide-angle view, so you can see the telescope in the observatory dome. And something that's interesting about it is unlike many telescopes, you notice it's very compact. It's not a very, very long structure, and that's because of the unique optical system of the mirrors. We have a 2-in-1 primary tertiary mirror. So the biggest mirror of the telescope actually functions as the first mirror that receives light, but also the third mirror that receives light. So you can see in this animation, the light comes in, bounces to a secondary mirror, and then is sent back to the inner ring of the primary mirror. And folding up this light path allows us to make the telescope much shorter than some of the other older type technology telescopes that have been designed. We also have the ability to slightly deform that primary tertiary mirror to account for atmospheric conditions and gravity. So it's what we call active optics. And I'll show you a picture here of the mirror once it was coated. And it's a little bit confusing to understand, but if you look at the very bottom of the picture, you can see that wide L1 surface, the first surface that receives light. And then if you look closer in to the part of the picture near where this center person is standing, you can see that there's a different curvature of reflection, and that's that L3, that tertiary mirror that was shown in the previous animation. So to survey the sky, we're going to, every 3 nights, cover all the available sky that we're able to see. And this telescope system with the mirror, the camera, has to be able to move to the next image in just 5 seconds. So we're going to be taking lots of pictures of the sky every night at 30-second snaps. And then within 5 seconds, it has to slew and settle to be ready to take the next exposure. So we developed a telescope mount that is able to move very, very quickly because of that. We also have a special slit on this dome. It's wider than normal telescope slits. And this is to take advantage of that 30-second exposure. The telescope will slew to position and look out that super wide slit. And in the 30 seconds, the slit is actually slowly moving with what we call a crawling dome. So the time that the telescope is taking that 30-second exposure, the dome is slightly changing position so that when the next exposure is ready to be taken, the dome is in the correct position. And to optimize that combination of the crawling dome and the slit is a little bit wider than it is in many observatory domes. So our mission really is to capture the cosmos, and we're going to be doing that in 2 different ways. One way we're going to be doing that is by taking these continuous series of pictures, and by the combination of these large, wide field of view pictures, the ability for us to take many pictures per night, and its super deep sensitivity to the sky, we're going to be creating over time the greatest astronomical movie ever made. And this is really a new technology too. It's kind of pushing astronomers into accepting kind of a norm that we can observe objects that change in the sky very quickly and follow them over a long period of time in sort of a movie-like fashion. And the other thing we'll be doing, of course, is that we'll be using all 6 filters to observe the sky. And so over time, we will build these images together. And for the things that don't change, these coads over time, over a 10-year period of time, will allow us to see deeper and deeper. Now, all of this data requires an enormous infrastructure that had to be designed in order to transmit this data very effectively and very quickly around the world. So every 40 seconds, we have a new 3,200 megapixel image. As you heard in the last video, this is going to generate about 20 terabytes of data per night. And What that means is over the period of our survey, which is going to be 10 years of collecting data in a rather continuous fashion, we will create about 200 million images. And that translates into trillions of measurements on billions of objects. One night of data is so immense that if you had a typical laptop, it would take you about 40 of them to store all the data from one night. A typical raw image is about 12 gigabytes in size. So, a lot of people in previous times were used to going to a server and downloading data, but really our paradigm is shifting where we're going to be working with data in the cloud because it really doesn't make sense to download data when we're talking about so much data and such immense size images. Now, how that data gets from Cerro Pachon around the world is, first of all, it is sent to Santiago, and then by redundant systems to Florida, and then to the SLAC National Laboratory in California. At that point, SLAC processes the data, it identifies the changes, and for every change it detects in the sky, what we call an alert, it will issue a notice about that within a minute of detection. Data are also sent across the Atlantic to Europe for further processing and long-term storage. And we have two primary data centers, both in France and the United Kingdom. Now, I've mentioned a few times that we're going to be conducting a survey. And this survey is called the Legacy Survey of Space and Time. It's a 10-year survey of the entire sky visible from our location in 6 different filters that you will see over time will give us about 300 visits to every area of the sky and result in just an immense number of objects that will be detected during our survey. And this Legacy Survey of Space and Time name came from a reuse of our original name of the telescope, which was the Large Synoptic Survey Telescope, LSST. So once we renamed the telescope, we had a lot of LSST logo kind of things sitting around. And we had one of our staff had a brilliant idea to rename our survey LSST. So sometimes you'll see LSST mentioned in names like the LSST camera and the LSST survey. And that just refers to the survey that Rubin Observatory is poised to begin later this year. So looking at the sky every 2 to 3 nights for 10 years kind of gives you an ability to build a static map, but of course we'll be picking up many transient and changing objects in the sky. There are some areas of the sky will be imaging more often and some areas will be imaging less often. This map shows a little bit about those changes. When you look at building a survey, why collect the same data over and over again? Well, first of all, as we collect more data, we'll be able to see deeper into the sky. But I like to think of a survey as building a jigsaw puzzle. So when you have only a few pieces of a puzzle, you don't really see some of the large scale changes that might be happening. You don't really see some of the largest kind of patterns in the sky. But as you build more and more pieces into your puzzle, it's a lot easier to start noticing what those patterns in the sky are. And so this survey is good for that reason. Another reason surveys are great is they provide a lot of data for many different types of science. And we'll be making this available to everyone in the world. So not only are we generating a lot of data for different science types, but we're opening that data for the world to explore. Every night, we expect to see about 10 million changes in the sky. And each one of those changes will be called an alert and will be sent immediately world public. So these alerts will come a lot from objects we know about, supernovae, variable stars, things that change position in the sky like asteroids, but we're likely to uncover some very rare events also. And because these alerts are sent out as world public, it will give immediate opportunities for global follow-up. Now, this alert stream is accessed by what we call community brokers. So rather than coming to Rubin Observatory directly to get the alerts, we have a number of brokers that have been developed. These are software packages, and you can go to one of these brokers and optimize it for the kind of alerts you want to get. You don't really want to get 10 million alerts per night. Nobody can deal with that kind of scale. So maybe you just want to look at asteroids, and maybe you only want to look at asteroids above a certain magnitude. So you can kind of customize and filter that by using these broker services. Anybody can use these brokers. We had almost 30 countries involved in the physical or the software construction of Rubin Observatory. And across the world, that translates to more than 2,000 members of science collaborations. These are professional astronomers, engineers, statisticians that have worked to build Rubin Observatory. So beyond the science collaboration members, we are enabling data for everybody to be accessible. So how do people who are not scientists access the data? Well, first of all, we will be developing quite a few citizen science projects, and we're working in partnership with Zooniverse to do that. So if you would like to go through some of Rubin data and help participate in scientists making new discoveries, we will have a lot of Zooniverse citizen science projects available. Amateur astronomers can go to access data through brokers, and our Education and Public Outreach Department has developed quite a few materials for students and teachers, and these are all available free online for everyone. Our first citizen science project launched in June, and we already have gotten more than 2.4, or we are approaching 2.4 million classifications of comets on comet catchers. So this is just our first and only citizen science project that's available right now, because as you know, the survey has not begun. So this is using a little bit of data that was collected from our commissioning camera. And it was collected a little bit last year as we were beginning to test systems out. But once we get our data flowing from our surveys, we'll expect to have many more citizen science projects. So let's talk a little bit about the ways that Rubin is going to be transforming science. One way is that we're going to be working in partnerships with other observatories that observe at many different wavelengths and particles. And this is called multi-messenger science, when different observatories observe the same object at different wavelengths. We can build a more complete understanding of objects in the universe. In addition to working with these observatories just to build complete understandings of known objects, there will be transient events. There will be quick events that happen, and these are called targets of opportunity, where we'll have the ability to interrupt our typical survey schedule, slew to an area maybe where there's been a gravitational wave event reported, to see if we have optical component follow-ups. So likewise, Rubin might detect some things that other observatories around the world will take and use for follow-up. We are expected to be the very best facility in the world for gravitational wave follow-up, especially because of our wide field of view and our quick ability to change schedule and respond. There are really four main areas of science that Rubin Observatory is focused on, and the first one is dark matter and dark energy. Our telescope was named after Dr. Rubin because she was very involved in dark matter research. And one of the very first ideas about this telescope was that it would be used primarily to study dark matter. We're also going to be looking at a deep dive into our galaxy and its local environment, a solar system census, and as I've mentioned before, all the objects in the sky that are changing. So let's unpack these a little bit one at a time. We're going to calculate, or we're going to observe many Milky Way stars at a level that's been unprecedented before. So creating a map that's about 1,000 times larger than previous surveys, with eventually about 8 billion stars. This will help us really understand better how the Milky Way has formed and evolved over time, what the structure of our galaxy and the local environments are, including the dwarf galaxies that surround us. And by studying the Milky Way, we really gain a lot of insights into how all galaxies are forming. We expect to uncover 4 times more solar system objects than we currently know. Especially important in that would be these near-Earth objects, which could pose potential threats to Earth. And so we expect that we'll find a lot of these objects that have not yet been detected but are thought to exist. And finally, just putting the whole pieces of the puzzle together by cataloging all these new solar system objects, seeing where they are, what is the distribution, the sizes, it gives insights into how our solar system formed, and therefore how other planetary systems would form. If there is a Planet 9, our telescope is expected to find it. And so, a lot of people think there's a Planet 9 out there because of the unusual orbits of some of the objects in our outer solar system. Really good article from Scientific American last year about the search for Planet 9 and Rubin's involvement. Now, the way that we're going to find all these objects in the sky that change are by what we call difference imaging. So what will happen is that over time, Rubin has a map built up of things in the sky that don't change. But then when we see a change, we can compare it to the previous image and see things like objects that are changing in brightness, objects that are moving. So objects that appear for the first time that we haven't seen before. And by using this difference imaging technique, we can very, very rapidly generate these alerts. We know that most of the universe is unseen to us. And in order to understand better the nature of dark matter and dark energy, we have to have more data. And because Rubin will be cataloging over time about 10 billion galaxies, it will really give us a lot more information about where these galaxies are distributed and their interactions with each other than we've ever had before. And hopefully this will give scientists really great insights into constraining what dark matter and dark energy could be and what it cannot be. We're very interested in charting this whole structure of the universe. Recently, the Dark Energy Spectroscopic Instrument published an amazing analysis of 3 years of data that had 15 million galaxies in it. And you can see a screenshot here in the background of one of those graphics. Now compare that to what Rubin will observe. Instead of 15 million, we will catalog 10 billion galaxies. So imagine how much better our maps and our understanding of the structure of the universe will be over time. We're also likely to find rare and exotic objects, not objects that have never been seen before, but objects that are so rare we haven't been able to systematically study them. And so by cataloging more of each of these kind of rare objects, we're able to get an idea better of their nature. Beyond that, what a lot of scientists are really excited about is Rubin is going to uncover objects we've never seen before and cause us to ask questions we've never asked before. Challenging current theories is another idea. We might find that the data provided by Rubin Observatory really points a finger at maybe we don't have things exactly right. And that's a really exciting idea. So being able to look at what we will find in the universe and determining the new questions will be a great part of Rubin's science. I wanted to take just a few minutes to tell you what's happening now. And many of you probably are aware that on June 23rd of this year, Rubin celebrated its First Look event. Now, First Look is a time for us to just give a peek at the science quality images that are to come. So it really is not the beginning of a survey. That hasn't happened yet. But it's just a chance for everybody to see and whet their appetites about what will happen. And at that First Look event, we displayed for the world a few images. So this was what we called the Cosmic Treasure Chest. You can see it was made from about 1,200 images in 4 different filters. And this, if you imagine this, it's kind of a survey depth of what we would see after 5 years of observing the same piece of sky. But this was only taken in 4 filters, and Rubin, of course, will do it in 6. But in this one image alone, which is about the size of 2.5 pointings of Rubin on the sky, there are 10 million galaxies. The other video that I'd like to play for you that was premiered on First Look was some footage taken over just about 10.5 hours of time, where we looked at solar system objects primarily. Right now, we typically discover about 20,000 asteroids a year in the global community. In just 10.5 hours, Rubin discovered almost 1,900 new asteroids. So First Look was June 23rd. And between June 23rd and September 21, there were 23 weeks where we were undergoing commissioning. Commissioning is a time when you check out the systems of the telescope, you fix little things that need to be tweaked. You, for instance, like aligning optics, calibrating things, developing some base data that you'll use in the survey, refining things like the active optics system, testing the science pipeline, image processing, the alert stream. All these different things have been going on during commissioning, but that recently ended. So what's happening now is we have a period of time until October 24th, where there's a little bit of final maintenance and engineering going on before the beginning of the survey. One of the things that's happening right now at the summit is we're installing a light windscreen. There's a team from France that has come over to do some maintenance on the camera and filters. And so that's what's happening right now. Now, beginning October 25th, that's the official end of construction. And at that point, we will go into what we call early operations. But still, the survey doesn't begin on October 25th. There's just a little bit more time needed to get the final pieces in place, the final tweaks, and we hope sometime late this year we'll begin the survey. I'd like to take just a few minutes to talk now about our education and public outreach team. So we have a small team of around 10 people who are really the public face of Rubin Observatory. The developers, the graphic artists, the content specialists who have designed our website, worked very, very hard on our first look images. There is an education team and a data astronomer. And so a very small team of us are tasked with bringing Rubin to the world. So in addition to the fact we have a website, we've worked very hard to make everything mobile friendly so you can access all of our websites and materials on your phone. We have a very active social media campaign, and you can follow us on many different platforms, as you see here. The education program has developed free interactive classroom investigations that are online. They work very well at the high school and college level for students who are introductory students in astronomy. And this is just a screenshot of the 7 investigations we have available right now. And all of these investigations focus on just the very introductory aspects of stellar evolution and objects in the solar system, etc. For First Look, the education and outreach team developed a series of First Look resources for educators. There are a wide variety of materials there. We invite you to take a look at them. Everything from a Rubin coloring book to scaling activities where you can estimate the number of galaxies in the universe from a Rubin image. You can play Rubin bingo, or what we like to call Rubingo. So there are many other resources in addition to our investigations. We encourage you to take a look at them. So in short, I'd like to end by saying, get ready to be amazed. I'm very excited for the next 10 years to come. And I thank you for this opportunity for speaking to you today and invite your questions.
Thank you so much, Ardis. This was incredible to see. And I mean, seeing everything that the observatory has been sharing with us since the first look, and hearing your talk and learning a little bit more about the incredible things that the observatory is capable of. To me, is one of the most amazing things that I've seen in the past few years of how to reach people, which is probably some of the questions that I'm more interested about, because there's so many things happening in this observatory. Definitely has very incredible and amazing parts, but personally, the ones that I'm more interested in, the ones that immediately got my eye when I started learning about it, is how your team, the outreach and education and communication team, are developing all of these materials from this incredible, very specific data and this specific kind of science into something that the general audience or someone who's maybe not as specialized or have all this astronomy content, and they can understand it. And to me, it was such an important thing when I went through the website the first time and I started seeing every single small detail that is perfectly well designed and prepared to reach different audiences. And I talk about this particular thing because it's within the Office for Astronomy Outreach. This is exactly something that we have been having a lot of discussions lately in understanding how can we promote or can we bring more access to astronomy to everyone in the world, because this is something that is maybe for us is very normal because we are already part of the astronomical community. But the reality is that there are still many nations and many communities and many people in the world who don't have access to it, not because they're not interested in that. It's basically because the specifics of many other realities in many different countries are not the same. So for us, it's very important to talk about how can we bring astronomy to everyone, and how can we make it accessible and easy to reach. And I think this is specifically one of the things that the Vera Rubin Observatory has been doing incredibly, and your entire team in doing all of this. So I would like to know a little bit more about these incredible resources that you have, educational speaking, and mostly if you have any particular idea that you started developing because I know they're mostly for schools. You have many things for schools, which is something very important, and you have a lot of materials for teachers. So I would like to learn a little bit more about this, have this big experience being a teacher yourself.
Okay, thank you. Well, first of all, just speaking for our whole team, something we felt very important early on was that our entire outreach would be online. And the idea of making our entire outreach online is so that it is accessible to everybody, as opposed to, making things where you have to have physical materials to be able to do activities. We wanted to make sure everything was online so that it would be at no cost to anybody, and it could be downloaded. And because of the magic of technology now, much of what is on our websites can be easily translated, right? By just using a modern browser. And so although our primary mission was to develop all of our materials in Spanish and English, because our observatory, of course, is a US observatory, but it's located in Chile. So we wanted to make sure that was available in those two languages. What we have found in the years I've been working, especially with educators around the globe, is very high interest in these materials, much higher than we thought it would be, and much more beyond English and Spanish audiences. So that was a pleasant surprise. As far as how we developed our educator materials, first of all, we began with just a few of us who have a lot of experience in education, designing what we thought would be some of the topics of most interest and most help for people. But then we invited groups of teachers to join us for meetings where we sat down for 2 or 3 days together and used these focus groups to identify what were the highest needs. And from those highest needs, we worked to develop an outreach that would be for what we would say a typical student or teacher. There are already many great materials online for advanced students or for teachers who are super good in their field and very advanced and like to do unusual and difficult, challenging things. But there weren't a lot of great materials for the typical teacher who has constraints on the time they have to teach something, their own personal time, because anyone who's taught knows what it's like to teach and how much time it takes. But also the material resources, right? We didn't want to make materials that would cost teachers money, cause them to have to buy and assemble things for their classroom. So we tried to make all of our delivery digital so that the teachers wouldn't have to spend any money out of pocket. They wouldn't have to spend a lot of time preparing to do an activity. You literally could take one of our activities and do it tomorrow in your classroom if you'd like to.
Mhm.
And so that was a very important piece to us. But I'll also speak to another element that I believe is really true for our whole team, not just the education folks. And that is that it's really important that our data is accessible to everybody in the spirit of what Dr. Rubin wanted. So that's why we've developed all these different platforms. The social media is a great, very active platform. The planetarium world, creating visuals and media kits for the press and for planetarium operators and educators. And in addition to our education materials, our citizen science projects are going to reach a lot of people who are not in schools, as well as the students who are in schools. And so I think over time, what you'll see is we are attempting to serve all audiences as best we can.
Mhm. Yeah, and actually, I do believe that you're doing it incredibly well. If our audience have not gone to the website of the Vera C. Rubin Observatory, I definitely invite you to go and surf everything that they have there, because it's a pleasure, I have to say, because not only is this incredible science that we can all learn, but to see the different ways that you can actually use it in understanding is one of the most beautiful things that I've been seeing in astronomy and in astronomy outreach and education, because this is something that to me is one of the most challenging things, is having all this very specific set of information of science and to transform into something that can be approachable, easy to understand, easy to use. And like you were saying, something that is not going to cost you like spending even more money, or even having to get another source of education just to understand this kind of resources. And that is very, very important, because it actually removes a lot of the walls that we usually have when we come close to astronomy or to science in general, because we tend to think, and this is something that I think there's a part of education that has been building around it, and how science has to be behind this big wall, and only the big names of the important people can approach this, and it feels like it's something very far away from us. But the reality is that is not, and I find it so beautiful that it is so well understood within the Vera Rubin Observatory, and remembering that this is an observatory that is in Chile, that is not just hosted by a country, but it is integrated in Chilean communities and Chilean cultures, and understanding the language, understanding the customs, and remembering that every observatory that is around the world is part of a community, is part of a land, is part of a geographical ground, that it is also very, very important. And this is something that as communicators, as people that we've been seeing you from outside, I think many of us celebrate a lot that this approach is coming from the Vera Rubin Observatory.
Well, thank you. Something I forgot to mention too about all of our education activities is that they all use real data. And anyone who has used real data in their classrooms before understand that often it's very challenging, because you need special software. You might have problems with downloading things. You might have to take extra time to teach your students how to do some specialized type of query to get ready to use the data. We've tried to make everything seamless, where it's cloud-based, there's nothing to download, you don't have to install any software. We've built in all of the data visualization and analysis tools into our investigations, so it is as simple as going to a web page and clicking start.
So related to this discussion of data, we do have a question in the chat on YouTube. So someone has said, in medicine, we say we only find what we're looking for. So the question is, can the algorithm, the analysis algorithm for Rubin, be ready to find something that we couldn't have imagined, or yeah, and worth analyzing?
I think as far as are we ready to find something we couldn't have imagined, the answer is a resounding yes. So first of all, if you want to think about the world of what the area of what changes in the sky, we're generating these alerts immediately, and it's up to the world to look at them and categorize them and find the unusual things to go study and focus. So those will come to the front immediately. We're not trying to screen out anything in particular. We're going to make everything available that we see for the global community to look at and study. But secondly, in terms of the static sky, over time, as we build up that picture and all of the data in all the areas of the sky, again, you know, the picture is there. And the challenge really is for us to extract all the information from it. This is why I'm glad the entire world will be able to work on it. Because, you know, if it were up to a small science team, there's no way, even using machine learning, that we could hope to really digest all of the information that's in these images. It's been fun for me since first look to see the questions coming into the observatory from people who have looked at our images, like our cosmic treasure chest image, and they'll find strange and unusual things, and they'll say, what is this? There's this red flash around a star. And you know, a lot of those are artifacts from putting the images together. But it's nice that people are looking at the image so intensively that they're noticing all these small things and talking about them. And so I hope that that will just continue.
Yeah, definitely. I totally agree, and I find that fascinating. And I know we are in a moment where AI is such a big deal right now, but I do still think that there's a lot of human eyes and the human part that can be incredible in how do we see the world, which is something that at least this model of AIs are not there yet to trying to see a little bit beyond what it's already there, like the specific data. And this is something that is a human sort of thing that can be related either to art, into, I don't know, different ways to understanding reality. And it's exactly something that you said earlier, like the questions that we haven't even questioned before, just because we didn't know those things existed, and maybe we will start finding them, and these ideas, the new thoughts are coming to us. So we have another question from the chat. Maria Santiago Cortez from Mexico, she's one of our national outreach coordinators in Mexico. She's asking, do you have some outreach material to program aimed specifically for women to introduce girls in astronomy?
I would say no, not specifically for women, but what we do have on our website is we have a section under our website where it says Explore. There is a page called Rubin Voices, and what these are staff profiles of different people who work in our observatory. And many of these are women. So that's one place where if you wanted to filter, you could start with that. And I just put the link to that in chat. I'm trying to think if there's anything else really specifically for women, but I can't really say much else except one other resource comes to mind. And that is, we have a short video about who was Dr. Vera C. Rubin. And it's a 2-minute video that is part of a series of animated videos we have that has been created to talk about Dr. Rubin's path in science and how she met with some resistance because she was a woman. And so specifically, that's the other resource I can think about. And I'll try to find a link for that video and also put that in chat for you.
Okay, we posted the link about the Explore the Voices on the chat. So we were wondering if anyone else has another question, because we are running out of time. A little bit because of me, I'm sorry about that again. But definitely it's been incredible to have you both here. We are very happy to start this 100 hours event with two incredible women doing amazing things for the community in terms of education, in terms of communication, and sharing what astronomy is with the audience. Something that we didn't talk about much is Shannon as the director of Planetarium, which is, like we were saying, one of the main very important stones on how do we reach astronomy, how do we bring astronomy accessible to our audiences. And we tend to forget this, and this is another one of the things that we are celebrating this year, is the centennial of the planetarium, not only because it's incredible having 100 years of planetariums, but because we want everyone to remember how much of an impact can have a planetarium in a city. There are many places around the world who don't have planetariums. Right now, the Office for Astronomy Outreach is based in Japan. And the first time I arrived in Japan, the first time I arrived in Japan, I realized that in Japan there are over 300 planetariums, and I could not believe that there was this amount of planetariums in this country, because where I'm from in Mexico, we do have incredible planetariums, but they're like very, very few, probably not even 50. And it's also a big country. So I remember my own personal planetarium from my hometown, which is the Morelia, El Planetario de Morelia in Michoacán in Mexico. And it's one of the most treacherous things that we hold as we were kids. And it's part of our culture as people who grew up in this city. And I know this is something that many people around the world cherish with themselves. So planetariums are not just this nerdy spaces for nerds like us to talk about space, but it's also a way to connect with other people, to create this sense of community, to remember that there's many things that we can share and that we can continue learning in many different ways. So this is one of the other reasons that we want to celebrate these two very relatable projects in how we bring astronomy to the different audiences in incredible and very beautiful ways.
That seems like a great way to plug 24 hours, Cynthia. So tomorrow, I'm trying to convert between many time zones in my head.
I know.
So, but we are going to have 24 hours of planetariums, a 24-hour live stream with people from planetariums around the world coming in. You can hear more about planetariums and how they're really great tools for teaching astronomy. And that will be on YouTube on this same channel, starting, I think it's technically tomorrow at this point for all of us. It's tomorrow for me at 11 p.m. Eastern. It starts at noon in Japan time, correct? And 2 a.m. UTC. Did I remember these right?
Yes.
Thank you.
No,
so
3 a.m.
3 a.m.
Yes.
3 a.m. UTC.
I was sharing my image so that we could see.
So if you want to hear more about all of that and wonderful things being done around the world, you can tune in whenever you want. And there is a full schedule on the social media of the IAU OAO if you want to try to catch anyone specific.
Yes. So it's going to be a very fun, long, and amazing weekend for we're going to have people from more than 50 countries talking in different languages, saying different ways on how they participate with their own communities. We're going to have other observatories. We're going to have science communicators. We're going to have stories. We're going to have scientists. And we're going to have fun, basically. So please join us. We're going to start at 3 a.m. UTC time in this same channel, OAO YouTube channel. There's another link that it's already there if you want to just like click on it, or just you can save it so that it will remind you. But the idea is that we will continue to do this entire event. This is what the OAO is doing of our two main events, but there are many events happening around the world because this 100 Hours of Astronomy is a community teamwork kind of event. So if you want to find what is happening in your own region, in your own country, in your own city, go to our events engagement map within our website, and you will find an astronomy event very close to you. So join us and celebrate, and let's continue to learn about what is happening in the sky. So thank you both. Thank you, Shannon. Thank you, Ardis. We will love to continue to learn more about you and more about the incredible things that you're doing. So thank you so much. And well, my name is Cynthia Duran. I am part of the Office for Astronomy Outreach, and we will see you soon. Thank you, everyone.
Bye-bye.
Okay, I'm ending them. Wait. This is where. No.